This is Chapter 7, Chemical Reactions and Quantities, and this is the final section, 7.10, which is Energy in Chemical Reactions. Until now, we've really been focusing on the material components of a reaction. In other words, which reactants go into the reaction and which products come out of the reaction, or really which atoms are involved in the reaction. But every chemical reaction that you come across also involves some change in energy between the reactants and the products. So for example, if you have a cold pack and you activate it, some chemicals combine in the cold pack and they absorb energy from the surrounding environment, including from your skin, which causes the temperature of the surrounding environment to drop. Okay? So this is an example of an endothermic reaction, where the reaction absorbs energy and causes the temperature to go down. In this video, we're going to learn about how to quantify that change in energy through what's called the heat of reaction, and then calculate how much energy in the form of heat is gained or lost for a chemical reaction, whether it's exothermic or endothermic. So before we go on, it's useful to remember that the SI unit for energy is the joule, and with the metric system, we can always add prefixes, so a much more frequently used unit is the kilojoule. Okay, which is 1,000 joules. So this unit can be used to represent how much energy is either lost or gained during the course of a chemical reaction. So generally speaking, when we want to talk about energy changes that happen during a reaction, we want to talk about the heat of the reaction. Formally, the heat of the reaction is the amount of energy absorbed or released when the reaction takes place at a constant pressure. This is the formal definition for a quantity that's called enthalpy, which is a type of energy, but we're not really going to use that more specialized term. We're just going to refer to it as the heat of reaction, which is a more common way of expressing it. So this heat, which is really an energy change, occurs at virtually every step of a reaction. We tend to think about a chemical reaction occurring in one step where you just have reactants transform into products. But really, it's a series of complicated interactions that occur at the molecular or atomic level. And so you have energy changes that occur at each step, right? So when reactants begin to come together and first start to interact with one another, they sort of change their energy. When you have bonds that break or other bonds form, that requires a change in energy. And then when the products form and then sort of settle into their environment and begin to interact with their environment in their own unique way, that can also entail a change in energy. So overall, the heat of reaction is a combination of all of these different energy changes at all different steps. And so we can summarize this by saying the change in the heat, or the heat of the reaction, which is really represented by this delta H, right? I say change because the delta indicates the change. You have the heat of the reactants and the heat of the products, and so the difference between those two is the heat of the reaction, or the energy change due to the reaction. So delta H is really equal to the heat energy of the products in some sense minus the heat energy of the reactants in some sense. I say in some sense because we're really talking about enthalpies here, but again, we're going to stick to just thinking about this in terms of energy at this level. If we think about energy changes during a reaction, it should be clear that there are really two types of chemical reactions. You have some reactions that release energy to the environment, and you have some reactions that absorb energy from the environment. So the first type of chemical reaction, where the system of atoms releases energy to the environment, is called an exothermic reaction. We can think about this in terms of a reaction diagram like you see here on the right-hand side. So to interpret this diagram, it's important to remember that the atoms are the same at the beginning and the end. Okay? A chemical reaction is really just a rearrangement of a set of atoms. So if we look at the x-axis here, which says progress of reaction, we can see that at the beginning of the reaction, we're over here on the left-hand side. Okay? So this is where the reaction begins. As the reaction proceeds, we move to the right, and so at the end, we have the end of the reaction, okay, the way the atoms are configured here. But the way that the atoms are configured affects their energy. So the atoms which are arranged in the form or the configuration that they have in terms of the reactants at the beginning of the reaction have a certain energy. Okay? So these are the reactants here, right? Because we're at the beginning on the left-hand side, and we see that they're a certain distance up. The y-axis is this energy axis. So they have a certain energy because of their configuration. During the course of the reaction, they are rearranged and they form a new configuration, which you see here, that we call the products. And so that's at the end of the reaction. And this new configuration has different bonds and possibly different charges or what have you. And so because it's a new configuration, it has a different energy. So when the energy of the atoms in the products is less than the energy of the reactants, then we have what's called an exothermic reaction. Okay? You start at a high energy and you end at a lower energy. That difference, the difference in energy, has been released to the environment. It's been subtracted from the system of atoms and given off as heat to the environment. Okay? So that means that heat is really a product of this reaction. Heat comes out of this reaction and goes into the environment. Okay? So this is always true for an exothermic reaction. The heat or the energy of the products is less than the energy of the reactants. And there's two ways, if we're writing a chemical equation, that we can indicate this exothermic energy. The first way is to just include that amount of energy on the product side, right? Because again, heat is released to the environment, it's sort of like a product. So we can include it on the right-hand side, which is where we put the products in a chemical reaction. Or if we don't want to include the energy term in the equation itself, we can forget about that, leave it out of the equation, and then just quote a delta H value next to the equation or related to the equation somehow, where we give that number. The trick here is that since we're talking about an exothermic reaction, this delta H is always going to be negative. Okay, so delta H is negative for exothermic reactions. And the best way that you can remember that is why this word that I used, right? I said heat is subtracted from the system of atoms and it's given to the environment. So since we're subtracting energy from the system of atoms, the delta H gets a negative sign. The other type of chemical reaction is the opposite. Okay? So in this type of chemical reaction, the atoms, when they are in the form of the reactants, have a low energy. Okay? So at the beginning of the reaction here, we have this system of atoms, and they're connected together in the form of the reactants with a low energy. And then at the end of the reaction, on the right-hand side of this graph, the same atoms are now reconfigured into the form of the products, and they have a higher energy. So if the products have a higher energy than the reactants started with, then the system of atoms has to have absorbed some energy from the environment, or energy has to have been added to the atoms in order for them to get there, and that is what we call an endothermic reaction. Now in this case, we're taking energy out of the environment. So energy is coming from the environment and going into the atoms. And so it's going in as a reactant. So if we want to show the endothermic heat of reaction in the equation, we would put it on the left-hand side, okay, where all of the reactants go. So the way you can think about this is you need nitrogen, 1 mole of nitrogen and 1 mole of oxygen to create 2 moles of nitrogen monoxide, but those material components alone are not enough. You need 1 mole of nitrogen and 1 mole of oxygen, and you need to absorb 180 kilojoules from the environment in order to create 2 moles of nitrogen monoxide. Or again, the other way to show this would be to leave the energy term out of the reaction altogether, just show the material components in the reaction equation, and then quote the delta H value next to it. So in this case, you would say delta H equals 180 kilojoules. But again, now we're talking about an endothermic reaction where heat is absorbed or added to the atoms, to the system of atoms. And so since heat is being added to the atoms, the delta H has a plus sign. Okay? So when the term is put into the chemical equation, you don't give it a plus or minus. You just always give terms in the chemical equation a plus, and you indicate whether it's endothermic or exothermic by which side of the arrow it goes on. But if you're talking about the delta H separately from the chemical equation, then you really just need a plus or minus sign to indicate whether it's endothermic or exothermic. Endothermic is positive, exothermic is negative. But now that we're looking at energy or heat as another necessary component of the chemical reaction, we need to start thinking about how it's related to the amount of the material components of the reaction. So just like there's a fixed ratio between the amount of one substance in a reaction and the amount of another, there's also a fixed ratio between the amounts of the physical components and the amount of heat needed for the reaction. So you can perform experiments where you determine exactly how much energy is absorbed or released during the course of a reaction. And that tells you for a given amount of product what the delta H is. And so if we know delta H, we can actually come up with, again, several conversion factors where we relate that energy change to each of the material components. Okay, so here we can see three conversion factors because there's three material components in this chemical equation. But each of these also has a corresponding conversion factor, which is just the reciprocal, where the moles are on top and the kilojoules are on bottom. Now, as usual, there is another complication when it comes to thinking about energy changes during a chemical reaction. So it's helpful to remember that every chemical reaction is, again, really a sequence of physical processes that occur at the molecular or the atomic level. Two of the most common processes, but not the only ones, but two of the most common processes are breaking bonds and forming bonds. And these processes involve a change in energy. So bond breaking always requires you to put energy into the atoms. Okay? In order to pull two atoms apart and break the bond between them, you have to apply some energy or add some energy to them. So bond breaking always absorbs heat. In other words, it's always endothermic. Bond formation is the opposite, and so bond formation always releases heat to the environment, and so it's exothermic. So between these two processes and some of the other processes that can occur, it can be very complicated to see where the overall reaction comes out in terms of absorbing or releasing heat. In general, if you have more energy absorbed during the various processes than is released, then delta H will be positive overall. It'll be greater than zero, and so you'll have an endothermic reaction. For an exothermic reaction, the net effect is that more energy is released than absorbed, and so the delta H is negative. It's less than zero. So this goes with what I said in some of the previous slides, where the delta H for an endothermic reaction is always positive, and the delta H for an exothermic reaction is always negative. Okay? That is the net energy change when you take into account all of the different physical processes. But what that means is that even when you have an exothermic reaction where heat is released to the environment, there's often a lot of energy that needs to go in the first place in order to sort of break the bonds or rearrange the atoms in such a way that they can then form the products. Okay? So even when you have an exothermic that releases energy, often you'll require some initial input of energy in order to get the reaction going. Okay? That initial input of energy that's required is what's known as the activation energy. So we can sort of modify those reaction diagrams that we saw to account for this activation energy. Instead of the energy of the reactants sort of just smoothly changing into the energy of the products, we have a bump in the middle. We have to overcome this reaction energy to get from the reactants to the products. Okay? So the activation energy can be thought of as the amounts of energy required to break the bonds in the reactants, but it's more complicated than that. There's a lot of other factors that contribute to activation energy, but that's a useful way for thinking about it for now. But when it comes to a reaction diagram, we should also think about it as a barrier, something that we need to overcome with enough energy in order for the reaction to proceed. Okay? So again, here you have an exothermic reaction where on the left-hand side where the energy of the products is lower than the energy of the reactants. But because of the activation energy, we can't just go straight from reactants to products. We have to go over this hill. We have to add some initial amount of energy first before we can turn them into products. So this activation energy is the difference between the energy of the reactants when the reaction first starts and the top of this peak here. Okay, it's hard to actually measure this, but we can just imagine that at some point they have the maximum amount of energy and then they begin to lose energy to form products. Okay, so this distance here, this difference in energy, is the activation energy. For an endothermic reaction, it's still defined the same way. So it's still the difference between the energy of the reactants and the maximum or the peak of this reaction diagram. So for an endothermic reaction, it tends to be a little bit bigger, okay, because you're starting from low energy reactants and then you're overcoming a peak to get to high energy products. Okay, so this has a pretty large activation energy on the right compared to this activation energy on the left. From these diagrams, we can also see how we can figure out what the heat of the reaction is. Okay? So the heat of the reaction is the difference between the energy of the products and the energy of the reactants. And so it's this difference. Okay? This arrow shows the heat of reaction. Okay? It's the same, or it's defined the same way for the endothermic reaction, where we have energy of the products and energy of the reactants, and we take the difference between them as the heat of the reaction. Okay? So if you're careful about how you define which one you're subtracting from which, then you'll get the sign automatically. But it's a lot easier to just look at the difference between them and then understand that for an exothermic reaction, that's negative because it's a loss of energy, and for an exothermic reaction, it's positive because it's a gain in energy. Let's look at an example where we need to calculate exactly how much energy is released during a reaction. So this question says, how much heat in kilojoules is released when nitrogen and hydrogen react to form 50 grams of ammonia? Okay? So we take nitrogen plus hydrogen and we create ammonia, and we're going to make 50 grams of ammonia, but the delta H for this reaction is negative 92.2 kilojoules. So let's begin to analyze this problem, right? Step one is to look at what we have. We're told how much of the ammonia product is formed in terms of the mass, and we're given the balanced chemical equation. What we need is to figure out how much heat is released, okay? And we know that heat is released because there's a negative sign in the delta H. So this negative sign in the delta H indicates that this is an exothermic reaction, which means that it releases heat to the surrounding environment. So the connection between the mass of how much product we got and how much heat was required, or how much heat was released from that, is this delta H. So we have to know that. But just like all of the material components in a chemical reaction are related in terms of their moles, when we think about the energy, that's also related to those amounts in terms of their molar amounts. So we are also going to need the molar mass in order to convert from mass to number of moles. So in devising the plan to calculate how much heat was released, we do recognize that the heat of reaction is what allows us to relate moles of product to kilojoules released. Okay, so in this case, for every 2 moles of ammonia that are created, 92.2 kilojoules of energy are released. Okay? Notice when I said that, I didn't mention the minus sign because the minus sign is implied by my saying that the energy is released. Okay? Again, the sign of delta H is really just a way of keeping track of which direction the heat flows. Is it going into the system or out of the system? In this case, it's going out of the system, it's released, and so we use a negative sign. Okay? So this heat of reaction, going back here to the plan, is the conversion factor between moles of ammonia and kilojoules released. Okay? But we're not given moles of ammonia, we're given the mass, the grams of ammonia, so we need the molar mass of ammonia to go from grams of ammonia to moles. Okay? So this is overall our plan. Looking at those steps, we see that we need 2 conversion factors. The first is the molar mass conversion factor of ammonia. Okay, so 1 mole of ammonia equals 17.03 grams. And then the next is not quite a mole-to-mole factor because we're not talking about 2 material components. We're talking about 1 material or physical component and 1 energy component. So instead of this being a relationship between moles, it's a relationship between moles and kilojoules. Okay? As I said before, this expression here means that for every 2 moles of ammonia produced, you release 92.2 kilojoules. Now, in this case, they left the negative sign in, and that's fine. You can leave it in if you want, and then your answer will have a negative sign in it, which should indicate to you that it was a release of energy. Personally, I tend to leave the minus sign off, do my calculations, and then just think at the end about which way the heat was flowing to decide whether or not to add the negative sign back in. Either way you do it, you should get the same answer. So now we can set up the calculation to make the units cancel out and give us the answer that we're looking for. So we start from the mass of ammonia that was given, and the first conversion factor will convert mass to moles. So the mass of ammonia cancels the mass in the denominator, and that leaves us with moles of ammonia. And then the second conversion factor is going to cancel moles of ammonia and leave us with kilojoules. And so we can just fill in the blanks, right? 50 grams of ammonia. The molar mass of ammonia is 17.03. That's what goes next to the gram unit. And then from the equation, we can see that 2 moles of ammonia, because there's a 2 here, releases 92.2 kilojoules of energy. Okay? And so when we do this calculation out, we get an answer of negative 135 kilojoules. Now again, if you gave this answer without the negative sign here, in my opinion, that would be acceptable because of the way the question is phrased. The question is specifically phrased as how much heat is released from this reaction. So if you just said 135 kilojoules is released, that implies the negative sign, and so that would be fine. It's as if you took money from the ATM, right? If I asked you how much money you took from the ATM, you're not going to say I took negative $100. You would say you took $100 out of the ATM. Your bank account released $100 to you. Okay, so in the bank ledger, that's shown as a negative $100 in your account. But when we're just talking and you say how much money you took out, you would not say you took out negative $100. You would just say you took out $100, right? The negative is implied by what it is we're talking about. So these changes in energy during a chemical reaction can help us to understand some simple everyday things like hot and cold packs. So in this example, we have a cold pack which has some ammonium nitrate in it, okay, and it's in a special compartment that's separated from the surrounding liquid water. And so when we break the cold pack or hit it or squeeze it, the compartment breaks and the ammonium nitrate mixes into the water. And this mixing is actually an endothermic reaction. Okay, so the ammonium nitrate absorbs energy. Energy is added to the ammonium nitrate, and we end up with a solution of ammonium nitrate. So this is a very simple chemical reaction where the only real change is that we go from a solid ionic compound to an ionic compound that is dissolved in water. It goes from solid to aqueous. Okay, but even in this simple change, you have an absorption of energy. But a lot of students, when they first encounter this, it seems counterintuitive. Okay? You're taking a substance and you're adding energy to it, but I call this a cold pack, right? So if I'm taking something and adding energy to it, at first it seems like it doesn't really make sense that it would get cold. What you have to understand is that we're talking about adding energy to the system of atoms and ions that make up the reactants. Okay? So the ammonium nitrate is absorbing 26 kilojoules. You're adding 26 kilojoules to the ammonium nitrate. But where is that 26 kilojoules of energy coming from? Well, it's coming from the surrounding environment. It's coming from the water, from the plastic, from whatever other material is around, okay? Including your skin. So your skin can transmit energy through the package container into the water and into the ammonium nitrate. So by absorbing 26 kilojoules from the surrounding environment, the ammonium nitrate is absorbing energy from the environment, and that's causing the environment to decrease in temperature. Okay? If you think about putting a thermometer in this, the thermometer is also part of the environment. It's not part of the system of particles. Okay, and so since it's part of the environment, the ammonium nitrate will absorb energy from the thermometer will lose energy, and the thermometer will decrease in temperature. Okay? So it's a little counterintuitive at first, but you just have to recognize that there's a difference between the system of particles absorbing energy and the environment, which includes you and any sort of temperature measuring device absorbing energy. Okay? So when the ammonium nitrate absorbs energy, it absorbs it from you, and so you feel cold as a result. For a hot pack, you have the opposite situation. So in this case, you have calcium chloride, and when the calcium chloride mixes with water, this actually undergoes an exothermic reaction where it releases energy. And so this is a little bit easier to understand, I think, where you have a solid calcium chloride and it turns into dissolved calcium chloride and it releases 82 kilojoules of energy, which means it releases that energy to the environment, which includes you or a thermometer, right? So if you're gaining energy from the calcium chloride dissolving, then you're going to feel warmer, you're going to feel hot. And so this is how a hot pack works. And so now we've reached the end of chapter 7 of chemical reactions and quantities. And so we've learned about how chemical reactions can be expressed in terms of chemical equations, how we can balance chemical equations, what the coefficients mean, how that can be expressed as mole to mole factors between the different substances in a reaction. We've learned different types of chemical reactions. We've learned about reduction and oxidation reactions as the loss or gain of electrons. And we also learned about heats of reaction, okay, how energy changes during a reaction. When you have an exothermic reaction, heat flows out. We have an endothermic reaction, heat flows in or heat is absorbed. Okay. Then we also learned about a lot of important chemical quantities, especially the mole. Okay, so understanding the mole and the molar mass, and specifically how the molar mass allows us to transform between moles and grams, are very important concepts. These are probably two of the most important concepts in this entire chapter. Okay, so we can use the molar mass to convert moles to grams or grams to moles, and we need to do that generally multiple times in a question if we want to calculate how much product or the percent yield or the limiting reactant. Okay, so all of these concepts are important for you to know after you're finished with chapter 7.